Good day, everyone. Let us quickly look at the parallel arrangement of resistors. Parallel arrangement of resistors. Now, when resistors are arranged side by side like this, in such a way that uh, the same end is connected to the same junction, like this, it is called parallel arrangement of resistors. So the resistors are said to be arranged in parallel. The resistors are said to be arranged in parallel. Now, let's say we have something like this, everyone. We have kind of resistor like this, and we have another resistor like this, such that you know we have end A and we have end B. So what am I saying? We have end A here, we have end B here, we have end A here, we have end B here, we have end A here, and we have end B here. So if all the end B are connected together at the same junction like this, and also the ends A are connected together at the same junction like this. So this kind of arrangement is called what? This kind of arrangement is called parallel arrangement of resistors. Parallel arrangement of resistors. So we can also have two resistors connected in parallel. And one of the very important things is that you have to be able to identify resistors arranged in parallel. You have to be able to identify resistors arranged in parallel. So resistors arranged like this also. So when two resistors A, let's say R1 and R2 are arranged like this also, then this is called parallel arrangement of resistors. Do you understand that? So this is how parallel arrangement of resistors is to look like, because you have to be able to identify that this is parallel arrangement of resistors. Now, what are those things that are very important in parallel arrangement of resistors that every student must know? Now, it is very important that you know that in parallel arrangement of resistors, the potential difference across each resistor is the same and is equal to the potential difference across the whole connection. So the potential difference across each resistor is the same. So what are we trying to say? We are saying something like this. The potential difference across each resistor is the same. This is what some people, students used to forget. It is very important that you know that this voltage, which is the potential difference across R1 is the same, across R2 is the same, across R3 is the same. You can see from this point to this point is R1, from this point to this point it's also R2, from this point to this point it's also R3. So meaning that the potential difference is actually the same thing. The potential difference in a parallel connection, please take note of that. It is very, very important. The potential difference across parallel connection is the same thing. The potential difference is the same thing. Thank you for that. So what I'm trying to say now, what we are trying to say is that the potential difference V, which is the total potential difference, so we can say this potential difference V, you understand, is going to be equals to the potential difference across the this R1 resistor, and it's also going to be equals to what? Potential difference V across the R2 is going to be equals to the potential difference V across the R3. So meaning that the voltage across R1 V1, the voltage across R2 V2, the voltage across R3 V3 is the same thing to the voltage across the whole connection like this. So what if I'm given like 20 volts, that the 20 volts, this V is equal to 20 volts. That means the voltage in R1 is 20 volts. The voltage in R2 is also 20 volts. And the voltage in R3 is also 20 volts. That's what they are talking about. So that is one of the things that you have to know about parallel connection. So now, what again? Now, the total current this total current here, this current is the total current entering this junction. So when the current gets to this junction, it is going to separate. The current is going to separate like this into I1, I2, and I3, depending on the the value of the resistance. So meaning that the current that is going to be passing through here, I1, is going to be different from the current that is going to be passing through I2. Is going to be different from the current that is the I3. Meaning I1 is different from I2, is different from I3. So now, because R1 is different from R2, is different from R3. So now, the total current I is going to be the addition of each of these currents passing through each resistor. So what am I going to say? We are going to say that the current, the total current I, is going to be equals to I1, is going to be equals to I1 plus I2 plus I3. Please, this is a condition that is very important that you have to know when dealing with resistors in parallel. You have to know that the voltage is the same and the current is actually different. Is actually different. So now the total current is actually equals to the sum of the individual current passing through each resistor. So now we know from Ohm's law that V equals to IR. I know this from Ohm's law that V equals to IR. So if I make my I, the subject of the formula here, so I'm going to have something like this. I equals to V over what? V over R. You understand? So this V over R, I can substitute it for for I. Anywhere I see I, I'm going to substitute it for I. So I'm going to go back. You understand? I'm going to go back here. I'm going to go back here and say this I is going to be V over R. Remember what we just derived just now? So this is going to be V over R. But don't forget that this voltage is the same voltage, is the same V1, is the same V2, is the same V3. So anytime I want to put voltage, I'm not going to change it because the voltage is actually the same. You understand? So for I1, it's going to be V over what? V over R1, because you can see I said R1. Why did I not say V1? Because we said here that V1 is equal to V. Do you understand that? So this is going to be plus what? It's going to be plus V. The V is going to be constant because the V is the same thing. So I don't need to say V2 because V2 is the same thing as V. So I'm going to say R2 here. You understand? Then I'm going to say plus what? V over R3. So what are we saying now? Now that I can actually factorize V out, so I can say 1 over R. You understand? 1 over R, because if I say V times 1, it's still going to give me V. So here is equals to V. Now, this V, I'm going to factorize all these because V, I'm going to factorize them out. So I'm going to have, at the end of the day, in brackets, 1 over R1 plus 1 over R2 plus 1 over R2. So that is, but can you see that we have V here and we have V here? So we can decide to divide both sides by V, and at the end of the day, the V will cancel each other. So V will cancel those. So this V we cancel this V. Then we can have 1 over what? 1 over R1, 1 over R. Now this R is actually the equivalent resistance. This R here is actually called the equivalent resistance, or if you like, you call it the effective resistance, or you call it the total resistance. So 1 over R2 is equals to 1 over R1 plus 1 over R2 plus 1 over R3. I hope you can see how this is what you're going to always use whenever you have, you have to add, you have to combine the resistors in parallel. Whenever you have to combine the resistors in parallel, this is what you're going to always use. You understand? So that's what you're going to always use. Now, I want to show you something. Let's assume that we have two resistors in parallel. We have just two resistors in parallel. Let's assume that we have just two resistors in parallel. So I hope you all understand this. So now let's assume we have two resistors in parallel. So if we have two resistors in parallel, according to the equation we just wrote now, it means you're going to say 1 over R is going to be equals to 1 over R1 plus 1 over R2. I hope you can see. Now, but don't forget that what we are actually looking for is this R. It is not 1 over R. So we can actually need to substitute for R here. Do you understand? So we are just taking the case of when we have two resistors. Now, what we are going to do is to find, we are going to have 1 over R, and at the right hand side, I'm going to find the LCM of this denominator. So that's going to give me R1, R2. That's the LCM, and I'm going to do like this. So R1 in R1, R2 is going to give me R2. R2 times 1 is going to give me R2. Plus R2, we cancel this R2. This R2, we cancel this R2. Or R1, R2 divided by R2, R1. R1 times 1 is going to give me R1. You understand? So, but now look at this 1 over R. You understand? I can actually turn it to R over 1. So I've turned it upside down. So what is at this right hand side also? I'm going to turn it upside down. So I'm going to have R1, R2 over R2 plus R1. But R2 plus R1 can also be R1 plus R2. You understand? It's the same thing. So meaning that the equivalent resistance when we have two resistors will be what? Is going to be R1, R2 divided by R1 plus R2. So that is for the case of resistors when you have two resistors in what? In parallel. Now, a quick example: if you have if you have resistors like this, you have resistors like this. Okay, I think this is not going to do. So let's say you have resistors like this. Connected like this. Two resistors connected like this. In such a way that this is actually, let's say, this is 2 ohms and this is 3 ohms. You understand? So, and you have to find, this is 2 ohms and this is 3 ohms. You have to find the equivalent or the combined total resistance. So what you're going to do, you don't need to say 1 over 2. Instead of saying 1 over R is equals to 1 over what? 1 over R1 plus 1 over R2. Because there are two resistors in parallel, so I'm going to actually make use of this equation at this left-hand side. I'm not going to disturb myself to be doing 1 over R1. So what I'm actually going to do is that I'm going to say, let's actually do it here. I'm going to say R is equals to, for two resistors in parallel, R1, R2 over R1 plus R2. So I'm going to have what? That's going to be 2 times what? 2 times 3 divided by 2 plus 3. So 2 times 3 is going to give me what? It's going to give me 6. And then 2 plus 3 is going to give me what? 5. So 6 over 5 ohms. Or you put it in decimal. So that's going to be the answer. Thank you.